Well, good morning. So we kind of finished up last time talking about GPUs and how to program them. There's a tiny bit at the end of chapter 4 that has to do with roofline plots and arithmetic intensity. That I figured I'd do just a couple seconds on here on that, and then we'll move into snooping. So when you're dealing with arithmetic intensity is a way to tell basically how many computations you're doing that are floating point operations, usually based on how much data they require in order to do those operations. So if you have something with a very high arithmetic intensity, you've got a lot of calculations that you're having to do, but you don't have to load a lot of data that's going on to them. So we usually take this by taking the number of floating point operations that you're having to do and divide it by the amount of data required for that section that's going in. So it's just, taking the ops divided by the data. Data is usually evaluated in bytes, and this is usually in some type of, ops per sec or something of that sort. So we'll just take it as the ops that you're doing total that's going on. And that's your arithmetic intensity. Now, when you, arithmetic intensity, when you plot this, so flops are floating point operations. Usually we do this as flops per sec. And usually now it's G-flops, gigaflops per sec. And then we rate your arithmetic intensity. Right, so usually you put your arithmetic intensity, if I can get one operation per, byte loaded 2, 4, whatever. Obviously the more, serious the calculation you're doing, the further up it's going to go. That's going on. And what you do for a roofline plot is you got your gigaflops that's on there. There's a theoretical max that your machine can handle. And let's say whatever the maximum, that's for what your architecture is. And that presumes that you have all the data already there, so that you're just able to feed the machine. That's what it can do. Now, in reality, you're not going to always hit that, because you might have a really low arithmetic intensity, which means you might require a lot of data, in which case you're going to be limited by how much memory or how fast your memory can load data in. And so you'll get a line that's based off your memory speed. The memory speed that's in there is in its bandwidth. So it'll tell you how many, for instance, gigabytes per second. That will determine your slope. So the memory speed in here, usually rated, if this is in gigaflops, usually you do it as gigabytes per second, is equal to your slope, m, right? So just think of y equals mx plus b. And in this case, we're running to the origin, right? So it's, b equals 0. So you just need m on this, so it just gives you the slope line. And that's carrying off, and since this has been rated in bytes, it's directly compatible with this being in bytes also. So you don't have to deal with converting from the data size of double precision or single precision. And what will happen for your particular architecture, these lines will meet at a certain point. And we call this the roof line of your system. And this is the peak that goes on. That's the point at which your system theoretically can operate at full efficiency of whatever's going on. So if you have an arithmetic intensity of less than that, you just know you're not going to be able to operate at full speed. You'll be operating somewhere below it as it goes on. So it gives you a kind of a way to evaluate how far your system is lining in here. That's going on. This is why, for instance, like on GPUs, we have special RAM that's for them. That's often called GPU RAM, because they actually enhance them so they have really high bandwidth, because there's such a memory requirement needed for them. So that's the basic ideas of what it is. And it's just a way to compare systems. To see for your particular operation, you can take what is your arithmetic operation, the intensity of your particular code, and you can see for any system, where is it going to line on it that's going in. Most people are in this line, although there are some that can go out 8 or 16 even, things of that sort. But I find it pretty easy. It's just a way to compare systems. You know, and the big features you want to see is where is that peak, how high is the peak, and how steep is this slope, and where it lies relative to the arithmetic intensity, which will vary with your particular code. It is worth noting though, I mean, to understand why that code is what it is, so that, you know, if you need to deal with them, you can at least read the chart and see how to do it. It gives you a pretty good comparison of different systems that's out there. You can look at it quickly, and if you see a really steep slope, you go, oh, this thing has really good memory operations that are going on. You know, and how high that maximum will tell you where. The further this roof peak is to the left, the easier it is to achieve it, which means the simpler it is to parallelize and achieve your maximum performance. So in general, people like to see, you know, a peak that's way over here, ideally. However, it is worth noting that no metric should ever be accepted blindly. So for instance, I can force the roof peak over by also lowering my overall performance. Right? So it'll be easier to achieve, but there's not much to achieve. I mean, what people are really wanting is they're wanting this line, that line to stay where it's at, and this line to get steeper, which means better and better memory bandwidth. If that's true, then yes, you're getting something great. But, you know, realize anything can be fudged. So you have to look at the kind of synthetical. But if you see a really high peak here, but the roof line is way over to the right, realize you'll almost never achieve it. So that's where somebody's given you a great CPU and did not give you a great memory system to go along with it. So essentially it's worthless. Anyway, that's kind of the idea behind that. It's pretty straightforward. That's why I don't want to waste a lot of time on it. If I had time last time, I was going to mention it at the end, but I didn't. The book has a good comparison where they do the i7 against an NVIDIA GPU, and you can see the features on them. They're both, I mean, both of those are kind of older as it goes, and the NVIDIA GPU is even, I think it's like a 280. It's the generation before the i7. But you can see that the GPU, you know, beats the heck out of the CPU, which is what you would expect. I mean, it's designed for a special purpose. A special purpose thing should always have an advantage. So, right. What we want to talk about today is getting into how do you handle multiprocessors. In particular, we want to deal with multi-cores that's going on. And we'll talk about dealing with off the chip stuff later. So right now, almost everybody is multi-core, which means I've got CPUs, let's say CPU 0. I'm just going to do 2 in here that's going, because that makes my life a little easier when I'm talking and drawing stuff. But obviously this will extend. For cores, there are some crazy systems that try to put up to 128 that I've seen of super lightweight ones that are in there. You know, this is kind of the idea behind Intel when they have their, you know, Knights Landing and Knights Bridge and all that kind of stuff that goes on. There are various Knights, one which is their coprocessor to compete with it. They're basically taking old x86 cores that are smaller, and they dump them in and hook them. Their first one used a ring architecture to communicate on, and I believe the next one is doing a cross bridge. The problem with the ring architecture, and we'll deal with some of this stuff when we get to the network side, a ring architecture, when you're communicating on it, has very bad bandwidth transmissions. So if you've got, you know, nodes hooked along the outside, if you need to send a piece of data, it's going to block the data for everybody else going along. So they ran into, with any type of thing, if they're independent processes and they only have to send answers at the end, that's great. But if there's any communication, you're going to be in deep trouble. And we usually rate this, and like I said, we'll get into this in more detail probably in a few weeks, by what we call bisection bandwidth, which is we just kind of cut the whole thing. We take a look what's the bandwidth, and you can see I really only have 2. which corresponds if I was sending something from here to here, I could go that way or that way. So bisection bandwidth kind of gives you an idea about how many routes you have to be able to get through here. And this has bad ones. So the later ones that go, kind of like a crossbar, a grid that goes in to do it, which obviously will increase the bisection bandwidth between the two halves. So in our case, we're going to deal with, kind of smaller scale systems that you might deal with on a full CPU. So the CPUs are going to communicate to their level 1 cache. Now, you usually don't want to do anything to the level 1 cache because the level 1 cache is needed to pretty much be dedicated to your CPU and just go extremely quickly. That's going on. Now, I'm going to do something wrong here deliberately. I'm going to just take this and say, let's imagine for a sec that we're just communicating directly onto the RAM bus and going to RAM, because we're going to do an example to show where the problem is, so we know what we need to build. So imagine both of these CPUs are running a piece of code that's going in. And let's imagine that there's two variables that we're going to deal with in our code, X and Y. That's going on. And X and Y are stored immediately right next to each other, and each of these caches have a block area. Whatever it is, 2, 4, 8, 16, I don't care how many variables per block. Just that it's a block, and no matter what you do, they're going to be in the same block. Now on CPU 0, I'm just going to call it C0, and I'll call the other one C1 for abbreviation. There's going to be a sequence of commands that come in. So imagine I have a read, and this one reads X. And then a little bit later, this one is going to read Y. All right? And let's say this one is going to write X that's going on, and let's say that this one is going to read X. Okay? And we're going to see what's going to happen to each one of these things as it goes. Now, this one I've put concurrent, and we'll see what happens when it's concurrent, and then we'll talk about what happens even if we push it after, and it won't help me any if I push it after. So it might look that I'm going, there's just not enough time. But I want you to be able to see two problems that go on here. Now let's say that X is initially 0 and Y is 4, just to pick some numbers. And we're going to write to X the value of, 17. Okay? All right, so we want to track what's going to happen inside each of their caches. I'm going to erase here, give myself a little bit of room, so that I can store what's going to be in the block for X and Y. So, I'm moving along, I hit the first time, this one reads X. It's not in here, so it's going to send the message out on the bus, ask for X, and it's going to get both X and Y, because they're part of the same block. So it gets 0 and 4 in there. Now it only cares about 0, and it does whatever it's going to do with 0. That's going to eventually allow it to calculate 17. Time progresses on. We're going to even assume that both clocks are perfectly synced. They're on the same chips, so that's not too bad of an assumption. So this one's going to come in and it'll read Y. So it's also going to get 0, 4, even though it only wants the 4. And it's going to do whatever it wants to do. Time moves on. This one writes a 17. Now, when it writes that 17, the question is, what does it do to the rest of the system that's going in? Now, regardless of whether that one writes out or not, this one is reading at the same time, and there's no time for this one to get here, for it to get over to here, and that one to come out and read. But notice, even if it did, this one's going to get a cache hit. So when it does this, it's going to say, hey, I've got this in cache, that's the value. It's valid. So no matter what this one does, and no matter how long it takes to write, this one says, I got X. It's right here, and it's good. And it'll read it in, and it'll get 0. So even if you were to move this one later, it won't make a bit of difference. So it doesn't matter how fast this one can write, or even if it does write. Now, this hopefully will illustrate the problem that goes on. This is when you start getting into what we call coherence and consistency problems. Making sure that the memory is consistent, making sure that it's coherent, that when you read these things you get the correct values across everything. How that carries through becomes really important, and coherence and consistency are big ways to measure the system. We're going to deal with a coherence protocol first that's going to deal with what's called the snooping protocol, because that's the easier of the two. Consistency has to deal with getting it timed better and making sure things arrive and what time they arrive. Joy of 8 o'clock. Get my first coffee of the day. All right. So does it make sense where the problem is? Okay. So we want to handle this area. Now, how could we take care of this problem? What we need is this cache needs to know that this cache wrote. And then we do need to also handle enough time period for that to write. So we've identified two problems. There has to be a big enough delay that I could tell it, right? But we can kind of at the moment accept it. If you're right on time, this one cannot assume that it's going to get this from some distant location, right? Think about this in kind of physical terms. We handle this all the time. If I were trying to make sure I get a sample in from somebody that I need to get measured and tested in the lab, and I've got a due date for a paper, I'm not going to ask them to send me the data on the same day the papers due. And there's no time to do anything, and if there's any delay in the mail, you're in deep trouble, and you don't know exactly when these are going to happen. Perfect syncing between commands, give me a break, right? You don't know that any of these got a delay that could have done them. They're out of order execution. You can't guarantee exactly when that timing is. So because of all those features within the system, you got to make sure these things have a decent enough separation that there's a chance for it to go. Or you have to put in something that's going to block this command from going until that one has finished. All right? So you either have to give it enough time that it's safe, guaranteed, or you have to put in like a barrier between them, or you have to put some type of semaphore, or whatever. Something to guarantee that data is going to get transferred across. And later on we'll do this by passing messages and all kinds of other stuff. Alright, so assuming that we've got enough time separation now between them, or a barrier or whatever. So the read is, I still have to, even if that happens, if I don't handle a way to tell this one, stop, I'm in trouble. Right? Now, my comment about the fact that we don't usually want to just do it right on here is nobody really does it this way, because these are on the same chip to us. If they were off chip, right? The SMPs you saw in the early 90s and things, where this was one chip and this was another chip, and this was communicating across your motherboard, then it would make this type of a model make sense. My comment on the other one was just kind of the way we usually handle it now is you've got, CPU 0, CPU 1, they each have their own cache for level 1, but at level 2 it's combined. So I guess technically I shouldn't say that that's wrong, it's just not what most people do that's going on. So this would be a dual core system. And then if I want to do stuff, I can actually use this cache to handle it. Now some people will divide this and allow communication between them. Sometimes they allow the barriers to be moved slightly, so if one has a more memory intensive, they can handle the memory intensive operations. I'm not going to worry too much on these because you can implement that similar to the type of communications we're going to handle here. So at least the idea of this will carry through. All right, so I need to be able to send a signal, and I need to be able to handle an update. So to do that, we gotta talk about a couple different things of where these go in. If you remember way back to when we talked about cash and things, actually this stuff probably was from your first course on it. We had two different types. One was called right through, and one was called right back. Alright, difference on these was usually that goes on, typically a level 1 cache was a right through cache that goes on, which meant when you were writing, you would update this one, but this one would immediately update the next level below it. That's the idea of a right through. A right back, you would update that particular level and it would hold it. And it would be called dirty, because it's now holding a different value than what's below it. So it's authoritative, and it can't just delete itself. It has to write the value back down before it gets deleted, because it had the correct value that's going on. Now, let me ask you a question that goes on. When would I want to do a right through or right back? Would I want to do, which one would I do it, like for instance, a level 1 cache? Yeah, right through is much better at a level 1 cache. Because this level 2 cache, right, we said this is on chip, so this is really close, it's fast. Your level 1 cache, a right through cache has less work to do, right? What it's going to do is typically it's going to have a queue to write to the next level down. It's going to update its value, it's going to throw the thing into the queue. It's supposed to be really paying attention here to make sure this is streamlined. It doesn't want to try to maintain, is this dirty, do I have to update things? It's like extra work. Extra work means it's slowed down. So this needs to be really fast and efficient, and right through gives you lightweight stuff. So this one we typically do right through. This one is right before it goes out onto a bus. This is where it goes in. This type of communication is very fast on chip. The bus is one of the fastest buses off the chip, but it's not as fast as the chip is. So I could potentially also have a whole bunch of different cores sitting off this. No guarantee, but I could, right? It's not uncommon for decent systems today to have 2 or 4 chips on your board that's going on. So you're doing some SMP stuff as well as multi-core. For instance, on TARDIS, we've got 12 cores per chip, and then we've got 2 chips per board that's going in. And I just did that. I could have bought the 4 core per chip one, but price point wise, I could get more on the 2 than I could on the 4. That was just what was, you know, economically that possible. I got more per money that way, and cheap is good. But it's not uncommon to see 4. You usually don't go too much above there because there's a lot of diminishing returns on the bus. But if you think about it, if each one of these is kind of throwing data out all the time, because it's right through, you know, how often do you hit instructions that have to read or write? Well, it's usually like about a quarter of your operations. That means if you get 4 of these, you're using, on average, 100% of the bus just for data operations. What do you do for instructions? Right? So you just too rapidly use up all your bus bandwidth. The advantage that write back has is write back reduces the traffic on the bus. So level 2 is usually sitting right above that bus, and that's why I was saying you don't want to do this. You want another level in, because that's going to be right through. You want another level that's going to be right back, and that level will protect the bus. Okay, so if you think about it in those terms, we've got a nice way of handling that protection that's going in. Okay, and it'll reduce our traffic on the bus, which will allow us to have multiple systems to what that bus is. Now, if you think about this, if I'm just doing under this, and I just think of this as a cache now, as opposed to necessarily one system, right? But it's just the whole cache, so it could be a 1, 2, it could be whatever. At that point, I could be doing communications between here, or I could be doing communications between these, and the same idea will basically hold. Right? You obviously have to change some stuff, and there's some efficiencies you can do. But the concepts of what you have to do will stay the same. And the neat thing about this is we're going to do communications on these by building little small automata. All right. So, since we've agreed that they're basically the same type of situation as long as we generalize it enough, I'm going to remove this one as it now just becomes a special case. Okay. So we still have that problem of trying to get the communication across. So I need to be able to mark these of what state is. Right now, inside this cache location, I have some extra information. So we're going to take this in a second. We want to string them on. At the lowest level, I know, in addition to my data block that's going to hold my different data values, I also have some various kind of control bits that go on. So you typically have the tag, and now we have the valid bit and the dirty bit for the write back. Valid tells me has it properly been loaded, that handles the startup problems, and has it been flushed from cache and things like that. The dirty bit will handle, have I written it back, and my tag handles the rest of the address for lookup purposes. Now, if you think about it, these two bits together, this says is it valid or not, this says is it dirty or not. But the dirty bit doesn't matter unless the valid bit does. Right? So I'm trying to say, check whether it's invalid, whether it's valid, and whether it's dirty as I'm measuring between these. So those are three states, 2 bits, I'm fine, but I'm treating them as separate as it goes in. What I'm going to do is kind of combine these together and just consider it as the state of the system. And, you know, I put this in just so you realize that this is kind of the same exact thing. I've got 2 bits that are going to be my state. I'm going to leave invalid as it is. I'm going to rename valid as shared. Because I technically, both whether it's shared or it's dirty, right? In both cases it's valid. So really valid covered both, and it was either dirty or not if it was valid. So to handle the case where it's valid but not dirty, I'm going to call it shared. If it's dirty, this is really that it's been M modified that's going on. So we're going to change the name that goes in. But this is kind of how it relates to the old one. So we're going to call this the MSI protocol. It's going in. Now, I have 2 bits, so I want to establish my system to be able to check the state of what's going on. And realize that since there's multiple data things, these state bits are for the entire block. So if you make a bigger block, you're going to have less of this you're going to have to do. But even as it stands, I'm only going to have a few states here. I'm going to have my invalid, I'm going to have my shared, and I'm going to have my modified. I might have to do this for every block in my lowest level of cache. And this is again why I say you don't want to do this on level 1, because it's just more stuff. Now this is actually operating in parallel, but it's just more things you're having to pack in. And I could pack that stuff to support the CPU better. All right, so we want to think about what's going to happen. But now I've got 2 levels of things. I could have commands or issues that are coming normally from the CPU, right? A read request, a write request. But I'm also going to have the cache looking at what's going on the bus, because that's where its messages are going to come. So maybe I'll actually pick from the bus as a different color. I'll try to color code our messages. What's going on? All right. So I could also get bus messages that are happening inside my cache. And it's going to have to respond to both. Since it's looking on that bus, we call it a snooping protocol. Right? Snooping is like somebody looking around trying to find stuff. So we're snooping, and when this one is going to send a message here, I'm going to be snooping. So I'm going to know that it sent that message. And if it relates to my stuff, I can update. So I'm kind of like looking at other people's mail at this point. All right. Let's handle first off what happens on the CPU itself. All right. If I'm invalid, I've got a couple things that could happen. I could do a read or I could do a write. So we're going to put RMW in, read, miss, write, miss. Those are going to be my basic ones. And red means on the check. If I'm invalid and I get a read, miss, right? Now, I'm going to have to do a couple things. But the first question is, what state do I go to? Should I go to modified, shared, or stay at invalid? Well, think about what it goes into them. If I'm getting a read miss, right, am I changing anything? You only go to modified if you're changing something. Right? If I get a read miss, am I going to be updating my cache so there's data in there? Yes. So I can't stay at invalid because it'll be valid, which means I have to go here. Okay? So I'm going to get a read miss. I'm going to go to the shared state. And I'm going to have to actually request that data. Now, there's a lot of, every company has their own little special messaging thing. Some of them send out a read request onto the bus, and they send an announcement to people and all kinds of other stuff. So to avoid what the particulars they do on them, I'm going to set as kind of my color for that one to be blue, and I'm just going to send, say, a read request. And that could involve a whole bunch of stuff, right? So I'm just going to put a read on the bus. That's saying, and whatever you have to do, there could be a couple messages for that. You're going to send them out onto the bus and say, hey, here's what it is. That will allow other people to see that I'm doing this and for what address. And it will also allow me to get my answer back what's going on. So the read on the bus will be, I send a message and I will get value back. So I'll then have the value and I'll be in the shared state. Okay. So that's if I'm in the invalid state. Now, what happens if I'm in the shared state and I get a read miss? Now, the first question you should ask yourself is, does it make sense to get a read miss if I'm in the shared state? Now, this is what throws everybody for a loop. And I know the first time I saw this many, many moons ago, I looked at that and I'm like, that's not possible. Because if I get a read miss, that would mean it wasn't there, but it's shared. But I was thinking about it wrong. Because we're talking, when we think like that, we're talking about the address. Saying that I got a read miss on this particular address. But what do you do if I get a read miss on my address, but the cache is full? Right? I'm going to have to load that in, but somebody else is there. So I got to kick them out. So the cache location is in a shared state, but with some other piece of data, a different block. I get a read miss on a block I care about, and now I need to pull that in. So when you get these misses, it's possible to get a read miss, but it's getting a read miss on a different block. But that block is in the space you're about to take. So it's possible to get read misses and write misses in any of these locations that's going on. And this is just because it's full. We call these conflict misses. So if I get a read miss and my cache is full, so I'm about to stick something in the shared state, do I stay in the shared state? So think about what each one means. This means there's nothing in that location. That means there's something, but it's the same as whatever is in RAM. This means there's something, but it's different from what's in RAM. Right? So if I get a read miss here, am I going to have something at the end of this? Right? At the end of the operation, I will have a piece of data, right? Because I'll load the new data in. Right? is it going to be modified, or will it just be the same as what's in RAM? Same as in RAM. So it means it's going to go like this. Right? Now, since it's the same as what's in RAM, I don't have to send the value there out. So I don't need to do the flush. But I do need to read the new value. So I still have to put a read on the new address, the new block that's going onto the bus. What if I've been modified and I get a read miss? So if I'm in modified and I get a read miss, that means it must be on a different block, right? So since it's a different block, it means I'm dumping this, right? And I'm just loading a new thing. So the loading the new thing will be just like any other loading data. So if I'm loading data from RAM, what state will I be in? Shared. So it'll do this. Right? Because remember, this is a new block. Old block was modified, new block is going to be shared. I have to write the old block out, and I have to read the new block in. So I'm just going to put that as a write and a read that's going on. And like I said, whenever you do these writes going out, there could be a bunch of messages involved, but I'm not worried about those. As long as you know the basic operation, you can look at whatever your architecture is and figure them out. So I've taken care of my read misses. Right? What if I have a write miss? Now, let's do the simple thing. Let's say I'm in modified and I get a write miss. So that means that cache is full, I got a miss, so it wasn't on the block that's in there, it's on a new block. Right? So I'm throwing that one out and I'm putting them in. Now, some of this is going to depend on whether, on write misses, you could be a write miss where you are going to allocate or no allocate. Right? So write misses, there are options. There could be write, allocate, and write no allocate. Let me address this one when we get into this, because this could be where some of the things, because I see some confusion on those. Let's say write allocate, that goes on. Write allocate means, you know, you're doing a write, it's not in memory, so I'm going to create a spot in memory for you. Write no allocate means you're doing a write, it's not in memory. Most of the cases, the last thing you do is you write. Okay? So that means you're probably not going to use it again. So why should I make space for it? Just dump it out to RAM or to the next level below me. Now this one is going to make things really quick for you, your level of cache, but it adds extra work for the level below you. This one gives more work to you, but it saves the level below you. So when do you think I might want to do this? Make it easy for me, harder on the level below me. Think about your cache levels that go in, right? CPU, level 1, level 2, right? I want to make it easy on me, hard on the next level, right? Who would care about making it easy on them, hard on the next level? The very top one. So we often do write, no, allocate here, because this one doesn't want us, it's got to be attentive to the CPU, right? Level 2 cache, shove it down, let it handle it. That's its problem. I've got to be quick on this response here that's going on. So we often do write, no, allocate here, because I don't want to waste the room, I'm small, right? I want to be responsive, it's not likely to be used. Write, allocate takes the extra work, but it saves the level below me. This is really critical on the interconnect, and it cannot tolerate a lot. So therefore, write, allocate makes sense at this point. So when we're considering this spot, right? Right allocate becomes likely what you're gonna deal with if you're dealing with a bus here going to RAM. If you're dealing with situations of these versus the cache level below them that might have to handle communication, the level above me is probably right no allocate. So you would have to kind of adjust this slightly if you were dealing with an internal. So like I said, they're similar, but they're not the same. And that's why I say it's important to think about how you handle these. I'm going to assume that I'm dealing with a bus here. And I'm going to do that because that's what the book does. So at least I'm following similar to their areas. So we're going to assume that we're going to allocate on a right miss. That's going in. Now, this, believe it or not, is going to actually create some traffic on the bus to allocate for it. Because there's actually two things going to happen when I do this. Since I'm starting at modified, well, I can actually start. Let's do the easier one here. If there's nothing there, all I have to do is write my stuff, right? So, and I said I'm going to allocate. I'm going to write stuff, so it's going to be different. But I've got a block, right? So if I'm writing to like this location inside the block, and it doesn't matter which one, I just picked one at random, you still need to have the rest of the block is good, don't you? So if I get a right miss here, I'm going to have to get the rest of the block, which means on the network, I've got to send out a read for the rest of the block. Right? But in addition to the read for the rest of the block, I need to tell all the other cache locations, if you have a value, you better dump it. Right? So at this point, we send out a message we call invalidate. So I'm going to send a read message and an invalidate message. And the read message will get me the rest of my block. And the invalidate message will handle that thing over here to say, your value on that block is not good anymore. Right? And that is what will take care of this problem. Assuming there's enough things or a barrier of some point, this one will invalidate. It will no longer be in cache. We'll still have a different problem that comes up, but we've at least handled the first portion of this. So I can send a message now that will take care of that. What happens if I get a right miss, but there's no room in the cache? And so I pick something to eject, and that one that I need to eject happens to be modified. What's the end state of that location going to be? It's a right miss, so I'm going to write. So will the final location be invalid, shared, or modified? It'll be modified. And it started at modified. Let me go with the right miss above, because I have less to write there than I do on the other one. So I'll take a bigger space for my next thing. Now, if I get a right miss, I've got to do several things here. The old location was modified, so I have to write it out. So I have to put a write for the old value. I have to tell everybody else they're no good anymore. So I have to invalidate for the new location. So I write the old location, I invalidate the new one on the others, and then I read the rest of the block for the new one. I get a lot of bus traffic that's going on. All right, what if I get a right miss and I happen to be in the shared state? So think about it, right? All I'm going to do is I have to empty out what was there and put in the new stuff. And then think, what's the final state of the new stuff? Modified. So it started here, it's going to end here. It was a right miss. Do I have to write out something that's shared? Just ask, is it different than RAM? It's in shared, so it's no. right? So since it's not any different, I don't have to write it, I can just throw it away. But for the new stuff, it is going to make sure, I gotta make sure everybody else knows I'm about to write, so I still have to invalidate. And I still have to read the rest of the block. Yeah. So these are the two classic things that could happen internal to the CPU. Right? And we've noticed it already took care of part of the problem that's going on. Now, I've created 3 commands, read, write, and validate, that are bus commands. You might have to respond to those bus commands too. Read is my CPU stuff, but what happens if I'm in one of these states and I get one of these bus commands comes through? I need to do whatever they say also. So let's think about, what if I'm invalid and I get a bus command? Right? Do I care? If you're completely empty, you've got nothing, and you find out somebody else is loading a piece of data, does it matter? No. So you're going to stay invalid, you're not going to add anything extra. So this is anything on the bus. Right? If you're invalid, you could care less. All right. If I'm in shared and some of the bus commands come through, I could have different things that could happen here. What if I'm in the shared state and somebody else reads on the bus? Does it matter if 2 people are shared? Not in the least. So if I see a bus read, I don't care. Right? Now, once I get to the other one, for my address, if there's a write that goes on the bus, we got to ask ourselves the question, is that possible? To get a write, look at where all the write commands took place on. I was in, modified, I wrote. I was in, modified, I wrote. Take a look at the ones that start from anywhere other than modified. Is there a write? Oh, sorry, that started modified. On any of the ones that started somewhere else, there's no write. You only have a write if you're in modified. But if you're in modified, to get to modified, you have to invalidate everybody else, which means nobody else has anything. So if you're in this state, it's impossible to get a write. That would actually be an error condition for us, because I can't be shared and they're modified. Now I'll put a little caveat. Sometimes people expand these. So there's 2 extra letters. Sometimes people add E and S. E is exclusive, which means I'm in the shared state, but I'm the only one who has it. Why did I put S? O. O means I'm modified, and other people have it, and they're consistent with me. That's going on. But I'm the one who's authoritative. I'm the one who has to worry about writing it back. They don't. Right? So that's called owned. Right? If you add these, you have to add extra states. And so you could be in that state, and there could be a write, and I'm there, but it's only if there's an O. And we'll sometimes make that its own special thing that goes on. But if I'm in owned, and that one clears its stuff out, my value would still be correct. Right? So it would still be fine for me to stay here. And it makes no sense in MSI, because it can't happen. If you're in MOSI, you add the O in, it does make sense and you could stay in shared. The owner's gone, but nobody else is modifying anything, so you're still consistent with RAM, so who cares? So that's kind of just a little side note, in case that one is weird. I haven't checked if the book includes that. The book does talk about these, but it talks about it afterwards, so they may or may not include that. What if I'm in the shared state and I get invalidate? So just think about what the command name means, right? It means I'm about to write to it, you're wrong, get rid of what you got. if I get rid of what I got, I'm going to go here. And I'm shared, so there's nothing I have to send. So no problems there, I just dump what I've got and I'm done. So we've now handled all bus communications for 2 of them. Now we get to the fun state. Right? So let's deal with, I'm in the modified state and I get a read request. Somebody on the bus says, I need that address. Right? Now, they are sending it out on the bus expecting RAM to respond to this. Right? But I'm the one who has the correct value. So, I'm now going to be sharing it with somebody else, which means I'm going to have to go over to this state. If there was an O state, I would transition to O and they would go to shared. But it would be similar. So this is if I get a read. Now, signals. Because I need to do a couple things. Number one, I need to send a write out on the bus because I've got the authoritative value. Now, a note on this write. There could be an extra command that goes along with this. When I write, it's highly likely that I would like RAM to update and I would like this to update. When RAM updates, depending on your system, it may or may not cancel its write to here. So I may also need to send a command to RAM to say, stop accessing your data. Don't send this out, because I don't want to send my value and then it send the wrong value and it overwrite. Okay? So I'm going to need to, as part of this write, say, stop what you're sending. I'm much faster than RAM. RAM's going to be responding in what's going to be like 100 cycles to me. So I got time to send this thing out. So I'll send it out and tell it to stop. I'll send the correct value. That could also be part of one operation. So I'm just going to call it write. Okay? But we need to note that that stopping needs to happen as it goes on. So I'm going to get a read. I'm going to send a write message that goes out. And we'll presume that will stop the RAM. It'll update RAM. And the other one is snooping. So it'll see data come out on the bus and it'll just get it. From its perspective, it's going to get its answer faster than if RAM sent it. So this will actually improve its performance. So that's actually a good situation for me in this case that's going on. So I get a read, I send, I write my data, I go to the shared state because there's now at least 2 of us that have this. Does that make sense? Okay. What if I'm in modified state and I get a write? Right? If I'm getting a write, then that means somebody else is writing to this. Now, in this case, I put the write here of staying on, because I didn't get the invalidate for the MOSI, whatever. If I'm in the O one, I would go over, in this case, they would be writing, so they would go to owner. So I'd have to go over there. I'm going to put my invalidate and my write here. And I'm doing this one because this one was just easy enough to tag it on. I could have honestly put that in either spot. This one is only special case for the O, right? And I'll put right here. This is for anything else other than O is allowed. This one is right for anything technically other than O. If it was O, I would go here, and the new one becomes the owner that's going in. But I'm going to put it here because I don't want to write an extra line. Now, that's the signal I receive. What do I send? Because they could be writing, I could be doing X and they could have Y that they're writing to. They need my modified X. So I have to do a bus write. So maybe I should put BW in front of this or something. I'll put a right over here. And we'll just note that's after the comma, so that's the message that we're sending. I have to write what my current state is that's going on. And that, just like this one, could mean telling RAM, you don't send anything, I'm sending them the block. Because I've got the current best block. And then I go to invalid. That's going on. If it was O, you'd go over here and you'd still do the right because they still need your information. That's going on. And then they would have this and they could then modify theirs as it goes. Does that make sense? So this kind of gives us our protocols we're handling. I've lumped a few of our things together here. If you look on the book, it's a little bit, I think they do each message separate, so I think they have 4 ones across here. But hopefully at the end, it makes sense why we're doing each of these. And it makes sense some of the addeds, the E's and the O's that go on. We're trying to just handle the swapping in and out. What we'll do next time, or if I get some chance, I'll do it offline and make a video recording, is to do an example with this. How do we use this protocol? But hopefully at least the protocol makes sense, why it's going on, and some of the weird stuff, how you get misses when there's something there. Hopefully it makes more sense now too. All right, that's it. We're done for the day.